Here we are with part 2, and now we're going to start doing examples. We're going to use our one equation for force acting on two charged particles, and we are combining that a little bit with some force diagrams. So some of this might be some old-fashioned review. We're going to look a little bit at just some common sense and logic, because a lot of this you can do if you really just think about it. A lot of things are very simple. And we're also going to talk about vectors a little bit. So the importance of direction. Now, we have a positive 1.5 nanocoulomb charged particle on the left, and we have a negative 2.0 nanocoulomb charge on the right. Concept question: will they go towards each other or will they go away? Well, one is positive, one is negative, so they will attract. So we know that they will attract. Regardless of what that distance is, they will try to go towards each other. So they're separated by 1.5 centimeters. And we're going to do a very quick, easy calculation. What is the force between those two particles? And we know that we have a new formula that we're going to use. So K times, and K is a constant, Q1 is the charge of one of them, Q2 is the charge of the other one, and R squared is the distance squared between them. And I am doing this on purpose in centimeters to remind you that it's important to be paying attention to your units. Now, we have to make little conversions to all of our units in this example, so let's go ahead and do that. So the constant, that's a given. You don't have to memorize this. This will always be on either a formula sheet or I'll write on the board or whatever. You will be given this. You don't have to memorize it. It's 9 times 10 to the 9th. That's K. That's our constant. One of our charges is 1.5 times 10 to the negative 9th coulombs, because if you look back, it's a nanocoulomb, so that's times 10 to the negative 9. And the other one is negative 2 times 10 to the negative 9th coulombs, because it's also nanocoulombs. And the distance was 1.5 times 10 to the negative 2 meters squared, or just meters, and then you square it. So we have to be in meters and coulombs, and that will give us the proper units. So if you take a second and look, all of the units will cancel out except for newtons. You have a coulomb squared here, and you have 2 coulombs multiplied together in the top to where they will cancel out. And if you look at the 9 times 10 to the 9th Newton meters squared, we have meters squared in the numerator, and then we also have meters squared in the denominator, so they cancel out too. So we're just left with force as in newtons, so that's good. And if you calculate all that out, you get 1.2 times 10 to the negative 4th newtons. Very small. Now, it's important to look at this here, this negative number. Right? That's not what I wanted to do. Look at that. That's a negative. So if it is a negative, and you plug in all the charges exactly how they are, positive or negative, if it's negative, that means the forces will attract, because that means one of those charges was plus and one of those was negative. Now, if this came out positive, that means you know they repel. And that is because they either are both positive, so positive times positive will be positive, negative times negative will be negative. The distance will never be negative, because even if it somehow was, you would square it, and it would be coming out as positive. And, excuse me, sorry if that scared you. And the constant, 9 times 10 to the positive 9, is always that, so that's always positive. So there you go. If it comes out as positive, then they repel. So if the force, I'll write this too. So that's not an F, that's an F. So if the force is positive, they repel. If the force is negative, they attract. That is ugly, but you get the picture. Positive repel, negative they attract. So that's if you pay attention to the signs. Now you can simplify this and just say, oh, it's positive, and I know which way it goes, and that's perfectly fine. We'll get to that. Now let's look at another example. Q1 and Q2. Now we know that they are attracted to each other. So the Fe here is just the electric force. And the electric force that the Q1 feels from Q2 is equal and opposite to the one that Q2 feels on Q1. So if you didn't catch that, I'm going to write it out. Now you remember this notation from a long time ago, that the electric force on Q1 by Q2. On Q1 by Q2. So these are the forces acting on the charged particle on the left caused by the charge on the right. That is going to be equal and opposite of the electric force on Q2 by Q1. You might remember this as something that was kind of a big deal in physics. This is Newton's third law, equal and opposite forces. It even applies to charged particles. I know what you're thinking. You're nervous, and you're scared, and you said, oh my gosh, what if there's 3 charges or more? Well, it's not that bad. Honestly, it's just like anything, you just have to add the totals together. So let's do an example. Let's say we've got Q1, 2, and 3. Q1's positive, Q2 is negative, Q3 is negative. Now, for this example, it is important to know that that charge and that charge will not move. They are fixed in their position. They will not go anywhere. Q2 is free to move. So we put this charge near 2 other charges, and we're going to say, okay, what happens? So what is the force on Q2? So that means we need to think about, okay, where are the forces coming from? Now we have a charge particle at Q1, and we have a charge particle of Q3. Now, they're both going to exert forces on Q2, but one will be repelling, one will be attracting. So if we look at the charge from Q3, there is an electric force on Q2 caused by Q3, and since they will repel each other, it's going to push it up to the right. If we look at Q1, it's going to try to pull it towards Q1. So there's an electric force on Q2 by Q1. Now I'm going to rewrite this on the next page so you can kind of see. Because what we have to do is we have to think about, okay, what's the total force here? Well, the total force is going to be the force on Q2 by Q1 plus the force on Q2 by Q3. Now, let me pause really quick and extremely emphasize this. You do not add those numbers together. So if one of them was 5 and the other one was 3, the total force is not 8. It is the vector addition. So you have to use trig and you have to break it into components and find out what the total force is. So let me say that again, because I know some of you are going to try to do this and you're going to say that, wait a minute, Webassign said I was wrong. Well, this is why. You cannot add vector quantities like a scalar quantity, because they are not pointing at all in the same direction. They are pointing at different angles. You need to take their components into account. But we'll do an example with numbers in a bit. So you have one force to the upward left, one force to the upward right. That means the total force, if you added them both together, it's going to be kind of upward. Now we're doing a lot of hand waving here. We don't know exactly because we never gave numbers or angles or anything, but we'll do that in a second. But we know that it's not necessarily going to just be the number value of F1 plus the number value of F2. It's going to be the vector addition. So you have to use some trig. But don't worry, we'll use some trig. Oh, look at that. Here's an example with some trig. Now, here's an interesting little setup. I've got 4 positively charged particles in a perfect square. And all those positive charged particles are the exact same charge. Then I put a negative charge exactly in the middle. The question is, what is the force, the total force, acting on that negative charge? Well, we have to look at this picture here and think about what forces are acting on it. So we have a force from the bottom left one pulling it down to the left, while the other positive charged particle is also pulling it down to the right, and then the charged particle in the upper right corner is pulling it to the upper right, and then the one on the upper left is pulling it to the upper left. Okay, so we have 4 total forces acting on this. So that means F1, F2, F3, and F4. So somehow adding all their vector values will tell us what the net force is. So the total force, the total electric force on, instead of 2, let's erase that. Let's say that's on the negative charge. So on the negative charge particle, it's going to be F1 plus F2 plus F3 plus F4, and their vector values, not total them together. So I have to strongly emphasize this because I know some of you are going to want to just add them all up. But we have to look at directions here. And if you look at directions, we have F1 and F3, they are pointing exactly opposite to each other. This is a perfect square. One is pointing to one diagonal corner, one's pointing to the other diagonal corner. So F1 equals F3. And F2 equals F4. You might see where I'm going with this. If they're equal, that means there's no net force. So F1 and F3 do not produce a net force. That's pretty good. That makes things easy. F2 and F4 also, they cancel each other out, and they do not produce any net force. So what's the net force? The net force on, and not 2, I don't know why I wrote 2, the net force on the negative charge is 0, because all the forces cancel each other out. And I know what you're thinking, and don't worry, I know you're on the edge of your seat. What happens when it's not 0? Well, let's take that same picture, but we took the 2 positive charges out of the bottom side. And we asked the same question. What is the electric force on that negative charge? Now we know at this point it's not balanced anymore because we took 2 charges out. So we know we have to actually do some math here. Now, I gave that this is a perfect square, and each side is 4 centimeters long. So we also need to think of, okay, what are the charges? Because we have 2 forces pulling on this thing, and there's nothing pulling it against it anymore, so we have to figure out what it is. Now, the positive charges are both. Now, both positive charges are 1.5 nanocoulombs. So the one on the upper right is 1.5 nanocoulombs. The one on the upper left is also 1.5 nanocoulombs. So they're each the same charge. That's not the total, that's each. And the negative charge is minus 6.2 nanocoulombs. So from that information, we could actually figure out what the net force is, the electric force acting on the negative charge. And the things we need to know are, how far away is it from both of them? What directions are they? Is anything cancel out? And then, if it does, what doesn't cancel out? So we have a force. Oh boy, I wrote all that way too fast. Let me back up. So we have, let's look at these one at a time. Now we've got one force, and if you were looking at that, you see what I'm probably going to do. We're going to do trig. But we have one force of F2 pulling up to the right. And I think it would be smart to break these into horizontal and vertical components. So we have a y component, we have an x component. So we have the y component of F2 and the x component of F2. Then what we've got is the same thing on the other one. So we have an x component for F1 and a y component for F1. So if we add up all the components, we can figure out what the net force is. So if we add up all of our y's and all of our x's, then we're good to go. So I'm going to draw a double line here to emphasize that there are 2 triangles here. And what we have is F2 and F1, and I realize I switched the sides, but let's just pretend that that's how it originally was. And it doesn't matter because everything is symmetrical, so one side is really going to look exactly like the other side. So on the left, we've got an x component pulling to the left, and on the right we have an x component pulling to the right. Then we have 2 components pulling up. So F2 is pulling up, and Fy is pulling up. And I realize I messed this up again. Oh my gosh. Okay. I need to get my x's and y's straight here. So that's F2y, and that's F1y. We have there we go. Everything's back to normal. So that's F2 and F1. Those are their hypotenuse C's, hypoteni, whatever we want to call that. And now we can do some trig. So we know that F2x and F1x are going to cancel because of symmetry. Because even though this is in the middle, we haven't figured out exactly where in the middle, but we know that in the x direction, it's exactly in the center. And if both charges on the outside are the same, they're going to pull the same in the x direction. So F2x and F1x will cancel out. Cool. Let's make it more complicated. So we've got the total force really is just going to be F1y plus F2y. So if we figure out what those are and add them together, that's our net force. Not too bad. And again, since this all is very symmetrical, we've got 45-degree angles, 90-degree angles. We have two identical triangles on the left and the right here. So that means both F1y and F2y are exactly the same value in exactly the same direction. So both added together is just going to be 2 times one of them. Let's just say F1y. We could say F2y, it doesn't really matter. But if we find one of those components, we double it, and that's our force. So, in case you didn't see, the angle up in the top here is 45 degrees. Because if you look at a perfect square and you draw a perfect diagonal, that's going to be 45 degrees. So F1y, the value of that is going to be F1 times the sine of 45. So that means the electric force is 2 times whatever that ended up being. Alright, so we got to figure out what that force has got to be. Now, the force here is at this bottom corner. We know that it's in the middle of a square, and we know the lengths of the sides, so we can actually figure out the forces acting on both sides of the particles. So our basic formula is this: kq1 q2 over r squared. But what is r? So we have that one side is 4 centimeters. We know that the negative particle is halfway down the square. So we know that halfway through the top is 2 centimeters and halfway down is also 2 centimeters. So we got a very easy triangle to deal with. We've got a 45-45 triangle. So we can figure out what r is by using a number of different methods, but I'm going to use Pythagorean theorem because I know that 2 squared plus 2 squared equals r squared, and the square root of all 2 squared plus 2 squared equals that. So r, the distance between the negative particle and the positive, is going to be 2.828 centimeters. Now, what we can do is we can figure out the force from one of those sides, and then we can find the vertical component of it, and then we can wrap this up and we can find the total force. So easy enough. So remember, it's going to be 2 times the y component, and F1 sine of 45 is going to be the y component, and then F1 is just going to be using the radius we just found. So we plug in 2 times our normal calculation, where that distance between them was 2.828, and then I converted that to meters, and then multiply by sine of 45. So all I did was plug in this entire chunk in as F1, as the force between the negative particle and the positive, in a straight line. And then the 2 times sine of 45 gave us the y component and doubled it. And that's what we were originally trying to do. So that number will turn out to be 0.15 newtons. So approximately, I had to round. So that is our force. And it is going straight up. So if you forgot what the picture looked like, we have is a positive here, and a negative here. And we had one component pulling up, the other component pulling up, and that total was this, 0.15 newtons. Okay, so as you see, you really only have one new equation, and we really just need to look at a lot of force diagrams and go back to trig again. So I hope that doesn't scare you too much. Now, this is the end of the video. I apologize for it being kind of long, but I will see you in class, and we will work through some more problems together.